Yeah, I definitely tell you to study together because other than even actually on the mechanisms, you were very close to the same, missing the same points in most cases. Especially for the first couple of pages.
Yeah. This one, I don't understand why it's oxidized. Isn't added another option.
We added a new carbon oxygen bond though. And so reminder that in OChem, we say if the compound been oxidized, we're talking about is there a carbon that was oxidized? So this carbon went to an oxidation state. The oxygen didn't change oxidation state. This carbon went from a, we zoom in on it real quick. So carbon gets one electron from each of the carbon-carbon bonds, gets both of those and none of those. So that gives it an overall oxidation state of 0. Versus same carbon on the right-hand side, one there, and none of those. So now it's a +2. So because it went from a 0 because the carbon went from a 0 to a +2, something else had to be reduced somewhere, but the carbon was oxidized. And in this case, it's not like the hydrogen, the hydrogen could have been reduced if H2 was a byproduct here, because the hydrogen's +1 here, this oxygen's -2 and it's -2, and we don't know what happened. Maybe the hydrogen was reduced, but the main point is that this compound was oxidized. So adding an entire another oxygen or some other electronegative element is definitely a clue, but it can be even without changing the atoms.
Yeah.
If it changed where the bonds are. And then you both missed this one too.
Yeah. Well, we did do it together. So.
Right. I can tell because you had the identical answer. That's fine. You're allowed to do that for these. So we did add an oxygen, and oxygen is more electronegative than chlorine, but in either case, either chlorine or oxygen is more electronegative than carbon, so it doesn't make a difference to the carbon. This carbon is a +3 because it only has one electron from the other carbon bond, and here is also a +3 because none of these electrons can belong to the carbon, just like over here. And then everybody got this one right. We added an oxygen, so that's easy.
And then you got the acidity question, right? So I assume that we're good on that.
Yeah.
And then bromoalkane.
Just means an alkane with a bromine on it. So I was just, I thought that was actually easier with the answer because it's just an SN2.
So like, does it matter which one you put in?
It
Like,
does, started with this, and if it was a specific stereoisomer, we know you pay attention to that. If we put it through SN1 with OH with hydroxide as the nucleophile, then we get this product. So for all of these, just start with bromine on something and then use hydroxide as a nucleophile. It's just in this case, because it specifically says racemic, we want to make sure it's SN1 condition. So that one was a bit of a review. But then this one doesn't have any stereochemistry. But and it has to go SN1 anyway, because it's a tertiary carbon.
Right.
And then this one we want it to go SN2. So this one we could react just in with hydroxide in a non in an A. Let's see, we want a polar aprotic solvent.
okay, so.
But if you just said this under SN2 conditions, that would have been fine too.
See, that's what I thought, is I thought it was stuff, instead of was like, we have nothing in our notes from last class about them.
Correct. Because it was a review question.
You can confuse too.
That's the tricky thing about OCHEM is we never get to forget anything.
Yeah.
We still have to remember all those other ones, even though we're not in that class anymore, technically. All right. So questions on oxidation states, making alcohols. Okay. Let's talk about another way we can make alcohols, which is through a reduction reaction. Start with the carbonyl reaction. Or start with the carbonyl compounds. If we use a reducing agent, we can reduce that carbon and go from this would have been a +2 to a 0 oxidation state. And you might remember this term back when we first learned about oxidation and reduction, and at least the way I always introduce reducing agents and oxidizing agents is that the language is really weird for seemingly no reason when you're in Gen Chem. The reason why we use these terms is because in OChem, all we care about is the carbon-based compound. So it doesn't matter that something else has to get oxidized. We care about what's happening to the carbon. So a reducing agent is going to be oxidized because the electrons have to come from somewhere. And an oxidizing agent gets reduced. But in the case of OChem, all we're looking at is the point of view of the carbons. We're going to use a reducing agent to reduce our carbon. Quick logic, logistics question. You can't make a tertiary alcohol with this process. Why? What would the carbonyl have to look like to make a tertiary alcohol?
Oh, no, never mind.
So a tertiary alcohol would be something like this. What would the carbonyl look like?
And it's like the OH is gonna push everything around it down, right?
Correct, just like, but similar to any other tetrahedral. So this reaction is taking carbonyl, breaking a pi bond and adding a oxygen hydrogen bond, right? So that means that the molecule that we would have to start with to make this would look like
So we're at like 5 bonds.
exactly. We'd have to start from a carbon with 5 bonds, and we don't want that. So we can't make tertiary alcohols this way. Which means tertiary alcohols are probably the hardest ones to make because we can't make tertiary alcohols from addition reactions either. Because addition reactions had to start from an sp2 carbon as well. Unless there's some amount of rearranging going on. So tertiary alcohols are actually probably the hardest alcohols to make from a logic, just a logistics point of view. All right, so we can use hydrogen as our reducing agent because hydrogen naturally will go from an oxidation state of 0 to a +1 pretty easily. So we do see this reaction happen where we can hydrogenate a carbonyl just like we hydrogenated a carbon-carbon pi bonds. But it's not very practical because even with platinum, palladium, or nickel as a catalyst, we have to get this. We have to do this reaction at something like 400 atmospheres, which obviously is tricky to do. Glass can't handle that, so we're looking at doing something in a stainless steel reactor vessel, and even those have issues. It can be done though, just from a reasonableness check. I want to say it's every 12 feet that you go underwater, it's 1 atmosphere of pressure. So 100 atmospheres would be it going down 400 feet, sorry, 1,200 feet. So going down 400 atmospheres would be like going down 5,000 feet, which can be done. But obviously it's not easy to do given that whole submersible disaster a few years ago. That's comparable to where they were going though. The Titanic is about a mile down, so that's pretty similar to about 400 atmospheres of pressure. So we can do this reaction, but that's some pretty serious engineering to get it to work. So obviously we want something that is going to work at a lower pressure. And so our go-to reduction agents are going to be hydride sources. Things where you have, instead of starting with hydrogen as a oxidation state of 0, if we can start with hydrogen in an oxidation state of -1, that makes it a better nucleophile.
Saying it starts at a -1?
Right, so if we look at sodium, this is a compound called sodium borohydride. And if we look at the charges on everything, we know what the charge on sodium is going to be. It's sodium, right? So we're looking at BH4 with a minus charge. So it's going to look like that. Hydrogen is more electronegative than boron. The reason we can't just do this with a carbon is because carbon is more electronegative than hydrogen. If we want a hydride source, we want hydrogen with a -1 charge or -1 oxidation state. We have to have a hydrogen attached to something that's less electronegative than hydrogen. So boron and aluminum are the 2 most common cases. Lithium aluminum hydride gets used a lot too for similar reasons. Hydrogen is more electronegative than the aluminum, so that gives you a way to just make H minus basically. Anything with a negative charge can be a pretty good nucleophile. So what part of this molecule would a nucleophile have?
Wouldn't bond break here, do they? Or do they have?
They can happen at the same time. The big difference though is that hydrogen as a leaving group is going to bring the electrons with it. It's not a proton transfer step because the hydrogen gets to keep the electrons. So either way, let's just look at it in terms of a hydride with a negative charge. What part of this molecule is attractive to a negative charge? What's the charge? What's the partial charge on the oxygen?
It's partially.
It's partially negative, so would a hydride be attractive? Yeah,
But wouldn't the bond next to it then? Bond is next to it, like carbon under it?
yes, there we go. Because the oxygen is partial negative, so the carbon is partial positive. Except we can't just attach the hydride there because that would give carbon 5 bonds. So what are we going to break to do that? So the double bond breaks and the oxygen gets to keep the electrons. So then what does our intermediate look like after that? We didn't move any of the carbons or the oxygen, broke the pi bond.
And the oxygen.
Bingo. So then what's the last step?
That was on the part that just on the carbon goes up to the sheet.
Can't do that because then we'd still be left with a carbon with a negative charge. The solvent can be any protic solvent. What does that mean? Yeah, it could be it could be one of these, including water. What does a protic solvent have? What is a protic solvent?
But too much of these ones.
Protic solvent is something that can lose a proton. So going back to studying for the midterm and panicking about where did the water come from? The water is just there. Yeah, water is just there. And when the water is just there, it's usually just there as a proton source. So any alcohol will work because any alcohol, including water, can be deprotonated that way. So we just needed a quick proton transfer step to finish things up. All right, so here's the prettier mechanism. It's still just two steps that we've seen before. Nucleophile attacks. It's just that we've never seen a nucleophile attack a carbonyl before. But it still follows our same rules. Negative charge is attracted to a partial positive.
Yeah.
It's just instead of this being leading group leads, it's just a pi bond that's broken instead. So anytime you're gonna reduce a carbonyl, it's gonna work pretty much like this. Anytime you're using a reducing agent, a hydride source as a reducing agent, is gonna look something like this. Your hydride source is just gonna be attracted to a partial positive. You just need a strong enough nucleophile that it can break that pi bond. Which turns out it's not actually that hard. Although it does depend on what type of carbonyl you have. Sodium borohydride can only be used for ketones and aldehydes.
It's for the NADH.
Correct. It's really the BH4
Because,
that's the actual reactant.
but the LIALH4 with the other things.
Yes. In fact, that's the next slide. Lithium aluminum hydride is way more reactive than sodium borohydride. They're both hydride sources, but this one is much stronger. So you actually can't let it be exposed to a protic solvent. If you let it interact with a protic solvent, you wind up just making hydrogen gas instead. It basically steals the hydrogen from the protic solvent. And you make hydrogen gas. We know when we make hydrogen gas, we're now making a flammable gas. And this is also very exothermic. You basically get, it says violently, but it heats explosively.
Okay.
So if you put lithium aluminum hydride in water, it's going to catch fire and then explode. So we don't want to do that.
Yeah, but this production has it.
As a separate step. So you can expose your lithium aluminum hydride to your carbonyl first. And then you bring in water when all of this is gone, or at least most of it's gone. So it's actually useful. We did this. Trying to think of what reaction it was. We did this where we had a little bit of something really reactive left. And we added water both as a proton source and to also use up our leftover reactant. So maybe I'm thinking of lavins. Maybe we have. Because we will use sodium borohydride in a reduction reaction probably next week. Right, but so the only difference is it 2 steps or is it all happening all at once? So if it was all at once, we just say NaBH4 in water, but we wouldn't have 1 and 2 because it just needs to be done together.
That is red product solvent.
Any protic solvent is going to have the same issue with lithium aluminum hydride. So LiAlH4 is always going to be in 2 steps. Right, and this is actually a really useful distinction that we can make. Because remember, our first thought was, okay, if we're trying to reduce this carbon, we can just hydrogenate the pi bond, right? So if we needed super high pressures. And the other thing about that is, if you do it under that high of pressure, you're going to hydrogenate any pi bonds that you have are going to get hydrogenated. So especially if you want to keep the alkene, but turn the carbonyl into an alcohol, these work much better.
We have names for these.
reduction via sodium borohydride and reduction with lithium aluminum hydride. Hydrogenation.
So I think it's like. We have to think about most. I think.
Let's think about that.
I mean, it's all going on the partially pause.
Exactly. And that's not really gonna change. There's gonna be some amount of preference if you had two carbonyls and you only put in 1 mole of sodium borohydride. It's gonna favor hydrogenating one over the other. Or reducing one over the other, but we would never really rely on that, 'cause it's really gonna give you a mixture of products. And you'll also. We should call it reduction. Reduction of a carbonyl specifically, right? If you want to make it as specific as possible. So you might also see this little caveat here: sodium borohydride can't reduce carboxylic acids and acid derivatives. So let's recap what that means. Aldehydes and carbonyls we practiced with a little bit. Right, they're both carbonyls. An aldehyde is at the end of a carbon chain, so it's got this hydrogen here, versus a ketone is the middle of a carbon chain. Our carboxylic acids and other similar groups that are called acid derivatives. They're all in their same category, because if you notice these ones, this carbon on an aldehyde is going to have an oxidation state of, it doesn't get any of those, it gets both of those. So 2, it's got 3 electrons. So it's a +1 oxidation state. And here it's a +2 oxidation state. For all of the acid derivatives. So that means acids, that means esters, that means acyl chlorides. Acid anhydrides, and amides.
So those 6 on the bottom are all acid.
Those are actually, there's only 5. This is 1 molecule. But yes, those are all acid derivatives. They all get classified that way because if we look at the oxidation state of the carbonyl carbon, it gets none of those electrons, none of those, and 1 of those. So that makes it a +3 oxidation state. And that's going to be true for all of these acid derivatives. All of the acid derivatives have the same oxidation state on carbon. So aldehydes and ketones look pretty similar, but they're their own different functional group because each of the carbons has a different oxidation state, but they're similar enough to each other. But all of these acid derivatives that are all +3 oxidation state, they're all going to react similarly. Right, and so when we look at reactions that involve carbonyls, we're pretty much always gonna break these up into these two versus the acid derivatives. And they have a class. Let me just look this up because I feel like I always say it wrong and I don't want to say it the wrong way to you. No, these ones down here are the acid derivatives. The ones at the top are aldehydes and ketones. And it's not coming. I believe that the acid derivatives are class 1 and these are class 2, but it doesn't really matter that much as long as we know that the acids and acid derivatives are all together and the aldehydes and the ketones are all together. And I'll figure out what our textbook terminology, our textbook uses for that during break. So sodium borohydride only reduces aldehydes and ketones. But if you remember what I was saying a second ago, this lithium aluminum hydride is way more reactive than sodium borohydride. So sodium borohydride can only work on aldehydes and ketones. But lithium aluminum hydride can also reduce esters and acids. It's an older meme, but it gets the point across. Esters and acids, and I believe most of the carboxylic acid derivatives work with lithium aluminum hydride. But you might need to convert them to either the acid or the ester form first. So I'll leave those ones up here. So remember, acid is an OH attached to the carbonyl, an ester is an oxygen, and then another carbon group. All right, so lithium aluminum hydride is basically the nuclear option. We overused almost saying. Sodium borohydride is a lot more preferable because it's less explosive and has a longer shelf life. We only use sodium borohydride once a year here, but we can still keep it on the shelves and it's still good a year later. If we bought lithium aluminum hydride, we have to rebuy it for a year because it's that unstable and shelf life is that short. Because one of the other issues with these hydride sources is if you've got a bunch of H- rounds with a -1 oxidation state, if you let it react with oxygen, that's also a problem because that oxygen gas starts oxidation state at 0, but it wants to be -2 and it's way more electronegative than hydrogen. So
like the oxygen instead of more than.
basically, yeah, your oxygen is going to steal all the electrons from the hydrogen. You're going to wind up making hydroxide and water and things like that, but it's going to be really, really reactive. You know, one of my analogies for electronegativity is like sharing toys with a bully. Having hydrides around oxygen gas is like sending a 5-year-old to school with pizza and then a bunch of hungry 8th graders come along.
Yeah.
It's not going to stay the 5-year-old's pizza.
Yeah.
So if you expose lithium aluminum hydride just with oxygen, it'll catch on fire on its own. So you don't even need the water. Water makes it that much faster. But all I can say, we don't really want to use lithium aluminum hydride. We can avoid it because it's such a dangerous thing to work with.
But it works better than Yeah.
Especially for acids and esters, for the acid derivatives. So there's some cases where we don't have a choice. We just are not going to choose those reactions for a lab here because there's two of you in this class and we would use it once a year and it's expensive and dangerous. So what do we get for our product here? This is now that which means we could have used sodium borohydride. Our product here to start, before we get into drawing the mechanism, our product is going to look like this. We just take the carbonyl and turn it into an alcohol. And this is a really easy mechanism to use. It's only 2 steps, and both of the steps make a lot of sense. There's nothing tricky about it. If you have aluminum hydride, hydrogen leaves, brings an electron with it, and attaches to the carbonyl carbon. And then you just need to make room for it, though. So then we get an intermediate that looks like this. Now this carbon has 2 hydrogens on it. We wanted to draw the carbons, or the hydrogens, in this case, to show that we added a hydride there. Can. So relatively straightforward. The new thing that we added was just that our nucleophile is a hydride. And we're breaking a pi bond instead of having a group leave when our nucleophile attacks. Is this one where we have to worry about any rearrangement happening? Could this rearrange?
It could, because of the, I gave you back to the oxygen to make like.
So what would that look like if we saw that? So if we started from the first intermediate. So you're saying this hydrogen could move over to that negative charge?
Yeah,
So that would look then like that. Then the carbon keeps that. So now we've got OH and negative charge here.
yeah,
If we have to choose, in both cases, everything's got a full valence. If we have to choose between putting a negative charge on an oxygen versus a negative charge on a carbon, what makes more sense? The oxygen, because it's more electronegative.
So we're not really gonna see any rearranging. And remember that when we were dealing with carbocation rearranging, it was all because we had that empty p orbital. That we could kind of drag a whole pair of electrons, including a hydrogen over. We don't really have that here because everything's already got a whole valence. And our negative charge is out on the oxygen naturally, so we don't need to worry about that. So this is actually a really simple mechanism because it has no rearranging, no most substituted versus least substituted, so Markovnikov doesn't apply. And it's a too simple two-step mechanism to draw.
Yeah.
So what's our product look like for B? Anything tricky about it? It's gonna do the same thing. Production reactions, they're not so bad.
It's gonna be the same.
The mechanism is gonna look identical. Hydride attacks carbonyl carbon, pi bond breaks, and then you protonate the resulting negative charge. So if we started from a carboxylic acid or an ester instead, still doesn't change anything. The mechanism looks a little bit different. Because basically, in order to oxidize or in order to reduce a carboxylic acid all the way to an alcohol, that's really two reductions. Because you have to go from a carboxylic acid to an aldehyde, and then the aldehyde to the alcohol. So it's going to be a longer mechanism, but it's the same basic step. Right, so if we expose this to lithium aluminum hydride, first step is the same. The difference here is that once we get to this point, we now have an intermediate that has a good leaving group. So the next step is just your leaving group leaves and you reform the carbonyl bonds. So then we're back to, we reduce the carboxylic acid to an aldehyde. But now if we have an aldehyde, now we can do the same thing we just learned on the previous slide to finish the step.
Yeah.
How do we feel about that?
That's fine.
Same mechanism before with one extra step. Which is this one. Alright, so we'll take a break here. We come back. Start writing out the mechanism for this one reacting.
Our end result looks like.
So our end result is going to look like. We added 2 hydrogens to this carbon. And turned the oxygen to an alcohol. So let's come back at 11. And start working through that mechanism. We'll leave this one up on the board. And then we'll write it again for C.
See, that's not labeled.
That's not labeled as C.
This is not C.
It's not labeled.
And at first I was like, is that what we're supposed to be getting? I don't. We get from those two.
Correct.
And this is another balance last time for that, but for the other, then so, and there's stuff that you have to do. They also write some. Yeah. I'm sure the president. They also Stephen interest. Last what you're shut on this, the monster is nice. It's not a more dress. I looked. It's pretty. Like. Yes, there's a great. Videos. These contracts on business stuff. Adjustments. This is the best I got. It's really neat. It's from good and adjustment. If it votes, she can celebrate. No, I don't want AI signs. I want to open it. I don't know. The upstairs hot dogs. I'll call you. If you find something yummy, I'll make it. Right. Hey, do you know which short of his office? He might be, we're just on break right now, so I'm gonna back soon. You guys usually find it afterwards, right? Just have a question about the I was looking at it. Yeah, I don't know which word it was. Sure, guys. I don't know either. Yeah, that, those we, you know, nowadays, that we best practice. What are you doing? Okay. So they also requested that we do the bylaws. It's 17 pages, they want to sell 60 hills, I think it's like, for this, like, but maybe it was. Well. John, what did you talk today?
Yes, you're okay. Perfect, thank you.
What are you doing? It's frozen. I like the way that this is definitely frozen, but love that. Okay.
Get a chance to try it on your own first?
Yeah.
Okay, do that, and then I'll start in a second. Start by adding the hydride, breaking the pi bond to make room for it. Then this is the one that resets us right away. Back to being carbonyl in your leaving group leaves. So then we have an aldehyde plus our leaving group, which in this case is a methoxy group.
Where's the ME from?
That one right there. I could also draw it like this to make it look the same, but that almost looks more confusing to just have a single line like that. Or you could also right after the filter, that works too. So then the next step is we simply repeat the same thing we did for the aldehyde before. So a hydride. Comes in and attaches. Now we've added 2 hydrogens on there. Which we don't need to draw, obviously, for a skeletal structure, but can't hurt. Then a quick proton transfer and we're home. So technically for this one, we actually need 2 alcohols. Because once we add the water at the end, this one will turn into an alcohol. So we make methanol, but we'll also make propanol. But when we're focusing on these reduction reactions, we're typically most interested in the carbonyl part, the piece that has the carbonyl. It's sort of the primary molecule, carbonyl. And then for A, we didn't draw out the mechanism, but it's going to be the same product this week. It's just not going to take as much lithium aluminum hydride to get there.
It's just gonna be like the ones.
Exactly. All right, so here's the cleaned up mechanism. This is drawn as an ester, but it's the same as if it's carboxylic acid. Hydride attaches to make this tetrahedral intermediate. Then we kick off the leaving group and go back to being a carbonyl, and then we reduce it again. So nucleophilic attack blocks the leaving group, nucleophilic attack proton transfer. And just because I can always tell where we are relative to other organic chemistry classes based on the memes that show up online this time of year. And so we're about a week behind other organic chemistry classes. We lost a week, but all the carbonyl memes are showing up right now. So that means that they covered the material last week. Lithium aluminum hydride exists, carbonyls, I'm in danger.
You should pop up on your feed.
If you've trained it properly, there's a couple of chemistry communities online that make a lot of memes. There's a chemistry instructors Discord that has a lot of memes on it.
Nice.
Reddit's pretty good at it too.
Yes.
All right, so let's talk about one more type of reduction. This one is going to be the same exact mechanism, except it's a different nucleophile. Instead of having hydride as a nucleophile, if we make what's called a Grignard reagent, which despite the name, I believe he was Swiss, not Italian. But Swiss speak Italian is one of their primary languages. And Switzerland doesn't have its own language.
Yeah, it's German.
They speak German, they speak the Swiss dialect of German, And then, or French or Italian, there's Swiss Italian, Swiss French as well.
Like how there's Spain, Spanish.
Exactly.
Yeah, Timon is from Switzerland. Yeah, we have a friend. And another.
Yeah. Well, that's why if you see a hockey player with a Italian seeming last name, they're almost always Swiss. Nothing against Italian hockey players, but they don't have the hockey culture the Swiss do.
Yeah.
Some the Wildland player Foligno, this that has that G in it. I don't think I can spell his name. Foligno. Anyway, Grignard, Swiss guy.
Yeah.
Grignard figured out that if you take a bromide and you expose it to magnesium as a metal, the magnesium basically inserts itself in between the carbon and bromine. Because the bromine is a good enough leaving group and more electronegative than the carbon, but the carbon is more electronegative than the magnesium. So what basically winds up happening is the magnesium, the bromine keeps the electrons, the magnesium adds a pair of electrons it gives to the carbon. But then that leaves the magnesium with a partial positive charge, the bromine basically sticks too.
So. The bromine piece and the comes back. No, the bromine piece and the Mg comes in, but then because the Mg is. Negative.
The MG had, let me see if I have. So I don't think this isn't a mechanism that
Is going to be on the exam. So it doesn't matter too much, but basically this magnesium has two valence electrons when it's metal, right? So basically magnesium comes in here and attaches those electrons to partial positive. And the bromine kind of keeps the electrons, or you can even think of it as also attaches to the magnesium. And so the magnesium basically gets inserted in between because it's not, the carbon is more electronegative than the magnesium, but not by too much. And the bromine is more electronegative than the carbon, but not by too much. So this doesn't work with chlorides, and it doesn't work with fluorides, and it doesn't work with other metals very well. There are a couple examples. Oh, you're right, it does work. We don't use chlorine very much. You're right. Thank you. The main gist though that we get from this is that now this carbon is a partial negative. Right, this is the first time we've seen carbon be a partial negative. Because it's the first time we've seen carbon make a covalent bond with metal. And so the result of that is that this carbon is now a nucleophile.
Is it the same on the right?
And same on the rings. This carbon gets a partial negative now, which makes it a nucleophile. Because the magnesium is also good. I guess the carbon is a good leaving group because it gets the electrons, it kicks the magnesium off as a positive charge. So if we have a carbonyl, well, our last night we just learned was a carbonyl when exposed to a nucleophile when it's that carbon, right? We just introduced a new type of nucleophile, but it'll do the exact same thing.
So now, like, we could use this in the same way we did when that one reacted and that analyst came off of it.
Correct. Exactly.
Added like.
You mean just like the hydride one, previous page?
No, the. August, it's not August. But the one where like you would have what you started with, then it had like 3 different branches and new stuff that you added.
Yes. Yes. This mechanism is gonna look very similar to the one from the previous page, it's just instead of adding a hydride to a carbonyl, this lets us add a carbon to a carbon. So it's still a reduction. Because we're losing carbon oxygen bonds.
Right.
But this winds up being a really, really helpful mechanistic, or sorry, synthetic technique. Because now we don't have to go through an alkyne to add carbonates. This is a new way we can change the carbon skeleton. That doesn't involve any triple bonds.
Yeah.
And it's really easy to make these. Literally, we're gonna do this, we're gonna do a Grignard reaction in lab. Maybe the beginning of next quarter, depending on timing. But making the Grignard reagent is literally you take this, take bromobenzene, and you add magnesium shavings to it, and you just let it sit. And it makes this.
So you just imagine these like disappear.
Yeah. We're gonna add an excess of magnesium to make sure we drive it as far as we can for its completion. But yeah, you just literally, the magnesium dissolves and forms this, which was, if this is a liquid, this is probably gonna be a liquid too, usually, or at least be soluble in whatever other solvents around. So it's really straightforward. The biggest issue with it is that these Grignard reagents that we make, so the Grignard reagent is the product that we then turn around and use the carbonate nucleophile. They're very, very reactive with water. So they don't have a very good shelf life because there's just moisture in the atmosphere. And so you wind up making them and then immediately using them. So we're going to do it. We got decent results the last couple of years where we make the Grignard reagent one lab period and then use it next lab period. So we'll do a 2-week-long synthesis where we start by doing this process and then we'll do this step.
The first step, is that could be our whole lab, or like, are we gonna start at sport on?
For representing how stable it is. Last where we have to make sure that it's totally dry. It's a lot more prep work.
But
If you ever done any painting on a house, the prep work is the hardest part. The prep work is harder than the actual reaction in this case because the glass were perfectly dry. Right, so once we make a Grignard reagent, we just add it to a carbonyl. So if we add it to a ketone, our R group attaches here, and this is rather than drawing magnesium and bromine, a lot of times we just draw the carbon with a negative charge. It's going to attack here. This first step looks just like the hydride step, though. But we attach an R group instead of a hydrogen. And then we follow up with a proton transfer. Which means this is how we make tertiary alcohols. Because we can't reduce a ketone with a hydride to make a tertiary alcohol, but if we added the extra carbon in, we can. Right, and even starting from an acid derivative like an ester,
we can do this twice. So we want to add the same R group twice. This is pretty easy to do. We just make two equivalents of this. This is so methyl magnesium bromide or a methyl Grignard reagent. And we just do it twice, and then introduce our water. This is similar to the lithium aluminum hydride. The water has to be a separate step. Otherwise, the water is going to react with the Grignard reagent faster than our alcohol, than our carbon will. The other nice thing about both this and the the hydride reduction reactions is that they do work. If we only included one equivalent of this, it would add one R group. And then we could add the hydride if we wanted to. So we can do these in either order, and we can, like, remember with hydrogenation, we want to do a partial hydrogenation, we had to be careful, we had to change what the reaction was with the dissolving metal or the poison catalyst. We don't have to do that with these reductions. We can do them sequentially pretty easily. Expose it to methyl magnesium bromide and then expose to sodium borohydride if we wanted to add a methyl group and a hydrogen. So these are going to be one of, basically the Grignard reaction is the number one go-to for synthesis where you need to add carbons to something. We learned about alkynes first sequentially because we were covering carbon-carbon pi bonds. This is much more powerful and much more common because almost everybody has bromomethane as a liquid in the stockroom. These are really, really common, and almost everybody has magnesium sitting in the stockroom. So it's not like the alkynes where if you want to react with acetylene, you have to go get a tank of acetylene where it has gas. This is already methyl or bromomethane is already a liquid.
I have a question for you about metals in my lab.
Okay.
So for physics,
Okay.
we were using tin. We were using multiple metals, but then one of them was tin. And then when we measured its density, all of the groups rated something very similar, and online was drastically different. So do what we have in the lab, is it actually tin, or is it like something different?
It's probably old tin.
What's the difference between?
So were you doing volume by displacement? You put it in water, and so part of it's I'm gonna guess that your densities were lower than online.
Yes.
So probably you didn't get all the water out,
Even if
or sorry, all the air out.
all the air out.
So when you put a bunch of irregularly shaped metal pieces in water, little bubbles cling to the little pores.
Not spheres, but like flat spheres.
But there's still gonna be like little areas where the surface tension of the water keeps the air in there. Unless you do a really good job. If we brought out the vortexer from bio, remember we use that thing you push down and it spins it. If you put your tin in a graduated cylinder, filled it with water, and then vortexed it to get and vibrated it so you get all of the air out, that would improve your answers. The other thing is if it's old tin's pretty reactive, right? So it actually, exactly. So you're actually measuring tin oxide and tin at the same time, probably with bubbles still attached as well. And tin oxide, they're gonna have, I'm guessing, but I guess that they have a lower density than tin as well. Most oxides are less dense than the metal.
Because oxygen.
Yeah, and they're not packed quite as tightly.
Okay. I'm gonna pass that in.
Yeah, so I would bet if you got metals that don't oxidize well, if you did it with copper.
Yeah, it was like copper, zinc, and one other one besides tin.
And zinc was probably pretty,
Beautiful.
really, so the
Yes.
zinc oxide is even easier than tin.
Oh, no, that's.
But maybe the oxide has close enough to the same density
Yeah, maybe.
that you weren't seeing
True.
a noticeable difference, but that's my guess. The air bubbles and the oxides.
Okay, thank you.
We are just, what did we measure yesterday? We did specific heat.
of metals. And so they were doing the same thing, except where specific heats don't quite match what's online.
Yeah.
Because it's a similar thing, because these metals are old and have been sitting in a jar and been used by however many people for how many years. They're just a little oxidized, which also typically means the surface is a little more porous and it's going to hold on to more of that oxygen as well. If you polished them up first, or soaked them in a dilute weak acid to remove some of the oxide, and then did it, you'd probably get better numbers. More than what you were asking for, but
No, that's.
no problem. So same first step, same mechanism basically, just with a different nucleophile. Carbon-based nucleophile instead of a hydride nucleophile. Attack carbonyl carbon and break pi bonds, and then you protonate. If this happens with a ester or an acid, it's the same mechanism we just saw too. Our group attacks, you make a tetrahedral intermediate and kick off the leaving group and reform the carbonyl. And you could, if you only added one equivalent to the Grignard reagent, you could stop here. And then add sodium borohydride if you wanted it to be a secondary alcohol. If we wanted to make it a tertiary alcohol, we're going to add another equivalent of that Grignard reagent. Make our oxygen with a negative charge again, protonate it. So same exact mechanism, just with carbons instead of hydrides. So if we want to use a Grignard reagent to make a specific compound, oftentimes there's more than one way you can do it. So in this case,
What's this phrase setting?
racemic
Yeah.
means R plus S. Means you're close to a 50-50 mixture.
Got it.
Which, if we think about this mechanism, we started from something planar. Right, I have an sp2 carbon. So this R group, the second R group that attaches, can attach from on top or on bottom. So we don't have any stereospecificity. We're going to get the racemic mixture all the time. So what could we start with and react with in order to make this?
We're just simple that. But we got different like start with this and hit.
No, this exactly the point.
We want to use the Grignard reagent though, right?
We want to use the Grignard reagent to make the tertiary alcohol here.
Right, so we would first put like the brown there the reagents.
Not quite. First off, so if it's a Grignard reaction, we added a new carbon, right? So there's 3 carbons attached right here. If we broke that piece off versus this piece versus this piece. So if I cut it at the black one,
We start with the one from like these slides before when we were first looking at reagents where it was the cycle with the healing on it.
yeah, we could start from bromobenzene. So what would be left if I had so we do this with magnesium to get our bromo, how did I say? Our phenylmagnesium bromide.
would be the common way to say it. Don't worry about naming Grignard reagents. So if this is our Grignard reagent, I know I just knew that there was a right way to say it, and I was trying to remember what it was. If we start with the benzene Grignard reagent, what would be left on the other side that it would have to react with? 1, 2, 3, 4 carbons. The carbonyl on carbon 2. Well,
He said, how would you?
How would you do it? so this is why I wanted to look at this, because there's 3 choices actually. Because we said, okay, well, what if we chopped off the benzene? What's left on the other side? So let's look at one of the other options. If it was the methyl group that was chopped off, then we would need to have bromomethane plus magnesium to give us our Grignard reagent, which then would react with the carbonyl that's left if you took this and oxidized it. So that would look like a benzene ring and then 3 carbons attached, right? So that's an option as well. What's the last possible choice?
Well,
So then we would need bromoethane with magnesium to make our ethyl Grignard reagent, which would then be plus 2 carbons attached to a benzene ring, right?
Yeah.
So, Taylor, to go back to your point, why did we pick this one? Or why would we pick any of these over the others? Depends on what's in our stock room. We now have 3 options. I don't think we have bromomethane in our stock room, but I bet we have bromoethane. And I know we have this in our stock room. This is 2-butanone or methyl ethyl ketone. If you don't have it in stock room, you literally go to the hardware store and buy it. It's a paint thinner, like acetone. The old school name for it is methyl ethyl ketone. So if you go to an old hardware or a hardware store in Nevada, ask for MEK, you can buy this. MEK is methyl ethyl ketone. The true name would be butanone, but that's not how they sold it in hardware stores. But so I know that we have this reactant, and I know we have bromobenzene.
we get it here and we add them together. Would you put water in there to get your OH instead of your O? Like,
Yeah, so
are you attached with your ring to your?
So you would add the water after this step. So this step is going to make the intermediate that looks like. So the blue intermediate. Is going to look like that. We've added the methyl group to the carbonyl carbon, but we haven't protonated it yet. So after we add the Grignard, after we do the Grignard reaction, the second step to the Grignard reaction is add water, which gives us our final product. I didn't leave myself enough room.
And because all of these start with the ketone or with the carbonyl being planar, you're gonna get a racemic mixture no matter which of these routes you go through. So this is, again, one of the reasons why it's so useful, Grignard reaction is so useful, is because you can literally say, okay, I have two options. Do I have any of this bromide and do I have any of this carbonyl? And if not, look at flipping them, look at what your other options. And you can do it in steps.
Can we finish the lab?
So it's gonna make the same intermediate. If we wanted to draw this, it would be those electrons come over here. And break pi bonds. And that's gonna give us the same intermediate.
Right, and then I want.
And then add water. Same for the orange one, same intermediate for the orange one, and then add water. I'm gonna erase this, but don't panic because the next slide is cleaned up version of what we just drew. So this is another case where color coding can help too and use these abbreviations because these all look the same. Once you break it up like that, oh, instead of drawing a benzene ring, I wrote pH, so I've drawn the ethyl, I do that. But if you say, okay, my methyl group is gonna be blue, my ethyl group is green, my phenyl group is gonna be red. As long as I have all three of them in a Grignard reaction, I'm gonna get the same product. And if we really wanted to start a step further back than that, you could start with benzoic acid. And add methyl magnesium bromide to turn this into this, which then we're right here. And then you can do the second step with the ethyl magnesium bromide. So we can add different R groups sequentially. As long as, and so the order doesn't even really matter. So the final yield. Final yield is going to be a little bit dictated by sterics, but for the most part, not really, because this is clean. There's plenty of room on top and bottom. So you pick what's convenient. I know for a fact, if we didn't have bromobenzene, know for a fact we have benzoic acid in the stock room. And I bet we have, if not methyl bromide, maybe methyl iodide, because I know that's a liquid at room temperature. So I have to go look up to see if an iodide substitute for the Grignard reaction. But it's certainly a possibility. All right, last slide. Let's do the same thing again. Yep.
Thank you. Like, that's what we want, can you just use one box?
Just from one step though. So you don't have to go all the way back to an acid. Start from A and aldehyde as appropriate.
It's like, replacing just another one.
So if we were
if we did this, if we wanted to turn it into this molecule, we would have to do it in 884. That would work, but this question specifically says linear. We want to add carbon, so we don't want to start here. But we could start as aldehyde. And then use methyl magnesium bromide.
But you want to feel like all three ways back home.
No, just one way. Just pick one. So this is the answer for A. If you wanted to switch it, you could start with ethanaldehyde. And then we'd be adding 3 over here. So then it would be the propyl group. The magnesium bromide. So it doesn't matter which. So for these questions, you find the carbon that has the oxygen attached to it. And then one of the R groups attached to your desired product has to start as the Grignard reagent, and the other R group attached has to be part of a carbon. So B looks really similar to A.
Yeah.
Except we added 2 methyl groups. We could either start from your first guess, Riley. You could either start here and do plus methyl magnesium bromide. You could do it from the, yeah. If you started from butanoic acid, you could do plus 2 methyl magnesium bromide. If we wanted to add 2 of the same R group, that's really easy to do. Start with the acid instead of the ketone. That would work as well. Both of those are going to give us B. So again, do I have 2 pentanone in my stockroom? Or do I have butanoic acid in my stockroom? They both should, I don't know, I'm gonna go look at my stockroom list, see. Which is why your final lab project in this class is, here's a stockroom,
Right. What we got?
what do we got? Exactly. And it winds up being kind of this fun logic puzzle, once you get like complete freedom with this little paralyzing. To just be, have a blank piece of paper and be told, go, figure this out.
Not like a similar one before. The last time we made.
So it's not gonna be, it'll just be a proposed, you're not actually going to do the procedure.
Are we gonna do it?
I've toyed with that before, but because we use so many reactants that we would only use there, we don't actually do the synthesis itself. We'll do a synthesis project. Actually, I think I might, the way this Open 3 is written, it might just be a poster present or a research article presentation. Once you've gotten through 2.5 quarters of OCHEM, you could go to the Journal of Organic Chemistry, pick an article at random, and you have the basis to be able to understand most of it. Yeah, we might have you do it together, or we might have you work together, but do, yeah.
Here they have that big, presentation that it's everybody, present it to everybody.
The thing is that, having had 2 full years of chemistry by that point and everybody else not having had OCHEM,
But that's the fun part.
that is part of the fun part. And so this is actually a really common thing in grad school is one of your first, if you're going into a PhD program especially, you go to they call it seminar. But it's basically a 1 credit class where you go once a week and you sit and you listen to people talk about their research. And if you're giving a seminar talk, and a lot of times there'll be people from other schools, stuff like that too. So they want to bring in somebody to teach us what they're doing. It's the first third of your talk, everybody in the room should be able to understand. The second third of your talk, half the people in the room can understand. In the last third of your talk, maybe only 5% of the room understands, depending if that's the area. So you start broad and then you narrow in.
Yeah,
So there's a lot to be said for being able to structure a presentation that way. That's not a bad way to do it for regular people. You just have to say, okay, if I'm starting for a bunch of people that never even heard of chemistry,
yeah,
you're starting even wider.
yeah,
And you might not even get to that last little bit, but you tailor your presentation for the audience. So that might be a good way to do that and still participate in the projects.
I get asked, oh, like, what do you do in organic chemistry? And I try to explain it in simple terms and they still don't get it. So I'm like, it's like just reactions, just like how we do things and how they work. They're like, okay, I don't get it. I can't put it in simple terms.
It's good practice though, because if you really understand something, you should be able to explain it to somebody who has. So it's good, like you found out when you were studying for your midterm, right?
Yeah,
Bouncing ideas off of whoever's in the front, or your rubber ducky that sits on your desk
yes.
is a helpful tool. All right. Last one.
I don't know if I did this one.
See, it's tricky.
Because it's on the end.
Because it's a primary alcohol. So realistically, we wouldn't use a Grignard reagent to make this.
Right.
We use sodium borohydride. But if we're forced to do a Grignard reagent, the only thing that's in our group that's attached is right there. So that means we'd be starting from our carbonyl would just be a single carbon. So formaldehyde. If we had formaldehyde, and then we have a propyl magnesium bromide. Because then it can still do the same thing, it's just we're only adding single carbon. Formaldehyde is not actually great to work with. It's not actually present in most cases as formaldehyde. It's actually present as a separate molecule. That has the same oxidation state that looks like this. Turns out if you put formaldehyde in formaldehyde, it'll rearrange itself a lot of times. But if there's even a hint of water, it rearranges itself to feel like this. So we actually wouldn't want to use this. We would start with the one with butanaldehyde, and just do sodium borohydride.
So I started with a purple with a bromine attached to it, then added magnesium so that it was, yeah, so I got there. But then I just added, I think this is where I was like pulling things out of the air, but I just added like a methyl alcohol to it.
So
And said, ta-da!
it wouldn't be alcohol because we need a good target. We need a carbon that can be reduced.
So you would have to start from here. And then that adds a single, the result of that though, gives you a single carbon alcohol addition. Alright, so those are actually the three reactions we added today. So sodium borohydride, lithium aluminum hydride, and then the Grignard reaction are three of the most important reactions for this next half of the class, and probably from here on out, especially for synthesis questions. Anytime you need to change the oxidation state of a carbon, your go-tos are going to be sodium borohydride, lithium aluminum hydride, or a Grignard reagent. So we'll end there. We'll do more practice with this on Thursday.
What? You made a book split?
We are doing a lab today. It feels like it's been forever because it has. It's been 3 weeks in a row without a lab now.
Yeah, we could have paper that, and then we missed the lab.
Yeah, even, and then paper lab, and then we did two. We missed two labs because we had the midterm
Oh, yes.
and then we had a snow day. So, yeah, so the lab is published. I don't think it's linked in the week overview, but it should show up on the assignments. Okay, the big thing we're looking at today is the idea of thermodynamic versus kinetic control. So the thermodynamic product is the one that's more favored at the end. The kinetic product is the one that has the lowest activation energy. And we can choose which product if we control the condition. That's what we're going to practice today. This is your go-to. This figure is what you want to be thinking about. And I'll see you in an hour.
Yes. They're going to touch up with the message.